Hey there, we're going to go over some orbit notes. And an orbit is just the path of a planet or a celestial body as it moves around another body. And so an example can be, let's say, the Earth and the Moon. And so the Moon is in orbit as it moves around the Earth. And a body that orbits another body, it's called a satellite. And a satellite can be man-made, like a weather satellite, or natural, like in this case, the moon. And orbits, they are elliptical, but for our purposes, we're going to focus on circular orbits, not elliptical orbits. And so, as we kind of go through here, um, we've started and we introduced what was a centripetal force. And remember, centripetal force is any force that's descriptive that causes an object to move in circular um, motion around another object. And in this example here with the Earth and the Moon, we discussed last time how Fg, right, that gravitational force between those two is what's causing the Moon to move in this circular orbit around the Earth. And so your Fg in this case is centripetal. And previously, we talked about our new equation for universal law of gravitation. It's equal to g m1 m2 divided by the distance squared. And we also discussed how a centripetal force is equal to mv squared over r. And when we have an object, a body that's in orbit around another, like the moon and the earth here, what we can do is we can set those two equal to each other, our Fg and this centripetal force. And when we do that, what happens is we end up with that gravitational constant times the mass, let's say the mass of the earth here, times the mass of the moon here, divided by the distance between them. And we can set that equal to this mv squared over r, where the mass of the moon times the velocity squared divided by r. And what happens is this mass of the moon cancels out, and so does one of your r's. And what I'm left with is gravitational constant times the mass of the earth divided by the distance between them is going to equal the velocity squared. And then we can solve for our velocity by taking the square root on both sides. So let's kind of look at a problem and work one together. This one says the Earth has a mass of 5.972 times 10 to the 24 kilograms. It's 384,000 kilometers away from the Moon, whose mass is 7.348 times 10 to the 22 kilograms. And we want to calculate the velocity of the Moon. And so let's kind of write out what we have. We have the mass of the Earth is equal to 5.972 times 10 to the 24 kilograms. We're given the mass of our moon, which is equal to 7.348 times 10 to the 22 kilograms. And we are given the distance between them, and that's going to be my r, and it's equal to 384,000 kilometers. Now be careful with the units there, that's kilometers. So to change that to meters, I can add 3 zeros to the end of it. So it'd be 384, 1, 2, 3, 1, 2, 3. And I could write that in scientific notation, and it would end up being 3.84 times 10 to the 8 meters. So from here, we're going to calculate the velocity of the moon. So like we said, our gravitational force is centripetal. So now we can plug in our equations that we have. G, mass of the Earth, mass of the moon, divided by the distance between them squared, is equal to mass of the moon, velocity squared, divided by the distance between them. And like we said earlier, that mass of the moon will cancel, one of those r's cancel, and then I can take the square root of both sides to get rid of that squared. And what I'm left with is that the velocity is equal to the square root g times mass of the Earth divided by the distance between them. And now we can just plug in our numbers. Square root 6.67 times 10 to the negative 11, and the mass of the Earth, which is 5.972 times 10 to the 24, all over the distance between them, which is at 3.84 times 10 to the 8 meters. And when you punch that in the calculator, you should end up with about 1,018 meters per second, which is really fast, right? Doesn't seem like it because it's so far away, but that's our velocity there of the moon. So let's go back up here. And one thing to kind of make note of is sometimes on the problems, what they'll do, let's draw, there we go. Let's draw the Earth. And let's say now we're talking about a satellite. Sometimes what happens on your problems is they'll tell you the altitude of the satellite. So it'll give you the distance from here to here. There's your altitude. And they're trying to get you to solve for the same thing. And we would solve it the same process where the velocity would end up being the square root of g times the mass of the Earth divided by the distance between them. But the distance, remember the distance r has to be from the center. Okay, so from here to here is your r. And so what happens sometimes on the problems, they'll give you the altitude and they'll give you the radius, and your r is going to equal the radius of the planet plus the altitude. So just pay close attention to those problems. Make sure they're not just giving you the altitude, because if they are, you need to add the radius of the planet to get your r to plug in over here. So just pay close attention to that over there. All right, another thing we're going to kind of talk about is we're going to try to understand why astronauts appear to float. Okay, if you see videos of astronauts, they're floating, or at least it looks like they're floating. And a lot of times we say, oh, there's no gravity. And so that's why they're floating. But that's not necessarily true. So let's look at an elevator example real quick. So let's say here's an elevator, and you're inside the elevator, standing on the floor, and the elevator is accelerating up. If we drew a free body diagram of this situation, you know you have your FG down, and since you're accelerating upwards, that means that you're going to have a larger normal force going up. So your normal force would be greater than your FG. Now let's look at another situation where you're in the elevator, and now you're accelerating down. Well, we have FG down, and so it would be the same size as it was in the first one, But since you're accelerating down, that means your net force is downward, so your normal force is not going to be as much. So your Fg would be greater than your normal force. And now lastly, let's look at another scenario. Let's draw our elevator. And now when you're in the elevator and the cable breaks and the elevator starts to fall, and it would be what we call free fall. And we talked about this during our kinematics unit. And if you remember, when you're in free fall, the only force is that Fg, right? Gravity is the only force. And if that's the case, then what would happen is that you and the elevator would be accelerating at the same rate, which would be at g. So your acceleration would equal g. And what it would look like inside the elevator is you would appear to float, because you'd be accelerating at the same rate as the elevator. And so in this case, the only force you have is your Fg, and your normal force is equal to 0. Because remember, in free fall, the only force is that gravitational force. You probably have seen a video that kind of demonstrates this, and that's from the Superman over at Six Flags. If you've seen some videos where people put coins on their knees and they're on top of the Superman, and then as soon as it drops, they're in free fall, both the penny and the person, and the penny kind of raises up and it starts to float, right? It looks like it's floating, but what's happening is that the penny and the person are both accelerating at g, right? So it appears to float. So if you never watched it, you can Google penny, with the Superman at Six Flags, and I'm sure you can find some videos showing that. And so astronauts in space, it's kind of the same thing. Okay, so gravity is acting on the astronauts, but they're actually in free fall because the only force that they're feeling there that's acting on them is gravity, right? Force of gravity. And so they appear to float. But when they're in their spaceship, both the spaceship and the astronauts are accelerating due to gravity, and so they appear to float inside their spaceship. And they're actually accelerating towards the Earth, but what happens is by the time they would have reached the Earth is curved away, and so they don't run into the Earth. A good example where you could see this is what's called Newton's canon. So on your computers, just kind of Google Newton's canon, and you'll see several different videos. But what it's showing is, it shows the Earth here, and it shows a large cannon. And there's even some PhET simulations, which we'll probably play around with in class, where you can see what happens to the object that you're trying to put in orbit at the different velocities. And if it's not at the right velocity, it crashes into the Earth. But once you find that the right velocity, it will stay in orbit around the Earth. So you had to find the right velocity to get that object in orbit and stop it from crashing into the planet.